this video, we'll learn about redirecting in pipes. So far, we've been using functions like printf to output data to the terminal, and functions like getString to allow the user to provide input to our program using the keyboard. Let's quickly take a look at a program that gets a line of input from the user and then outputs it. On line 7, we're prompting the user for a string, and then on line 8, we're printing it back out. Let's compile and run our program. Great. The string we provided was echoed back to us at the terminal. This happened because the printf function wrote to a stream called standardout, or stdout. When something is written to standardout, it's by default displayed by the terminal. So that's all well and good, but what if instead of simply displaying the string, we wanted to save it to a file? For example, we might want to remember exactly what our program did when we gave it a particular input later. One approach would be to do this in our C program, using some special functions for writing to files that we'll see in another video. Even easier, though, would be to somehow redirect standardout to a file. That way, when printf writes to standardout, the contents will be written to a file rather than displayed by the terminal. We can do just that by adding a greater than sign followed by a file name to the command we use to execute our program. So, rather than simply executing /redirect, we can run /redirect followed by a greater than sign followed by a file name, like file.txt. Let's see what happens. Okay, notice that this time nothing was displayed at the terminal, but we haven't modified the contents of our C program at all. Let's now examine the contents of this directory with ls. Alright, we now have a new file in our directory called file.txt, which is the file name we supplied when we ran our redirect program. Let's open up file.txt. And here, we can see that the standard out of redirect was written to the file called file.txt. So let's run the previous command again, but supplying a different input this time. Okay, let's take a look at file.txt now. We can see here that the file has been overwritten, so our original input isn't there anymore. If we instead want to append to this file, putting the new input below the existing contents of the file, we can use two greater than signs instead of just one. Let's try that. Now, if we open up file.txt again, we can see both of our input lines. In some cases, we might want to discard any output of our program. Rather than writing the output to a file and then deleting the file when we're done with it, we can write to a special file called /dev/null. When anything is written to /dev/null, or just dev null for short, it is automatically discarded. So think of dev null as a black hole for your data. So now that we've seen how the greater than sign can redirect standard out, let's see how we can redirect standard in, or stdin, the analog of standard out. While functions like printf write to the stream called standard out, getString and similar functions read from the stream called standard in, which by default is the stream of characters typed at the keyboard. We can redirect standard in using the less than sign followed by a file name. Now, rather than prompting the user for input at the terminal, our program will open the file we specified and use its lines as input. Let's see what happens. Great. The first line of file.txt has been printed to the terminal because we're calling getString once. If we had another call to getString in our program, the next line of file.txt would have been used as input to that call. Again, we haven't modified our C program at all. We're only changing how we run it. And also remember, we haven't redirected standard out this time, so the output of the program was still displayed at the terminal. We can, of course, redirect both standard in and standard out like this. Now, file2.txt contains the first line of file.txt. So using these operators, we've been able to read and write from text files. Now, let's see how we can use the output of one program as the input to another program. So here's another simple C program I have here called hello.c. As you can see, this simply outputs "Hi there" to the user. If I want redirect to use as input the output of hello, another program, I could first redirect the standard out of hello to a file called input.txt, then redirect the standard in of redirect to that same file, input.txt. So I can do /hello greater than input.txt, press enter to execute this, followed by /redirect less than input.txt, and execute that. So we can shorten this a bit with a semicolon, which allows us to run 2 or more commands on the same line. So I can say /hello greater than input.txt, semicolon, /redirect less than input.txt. So this works, but it still feels pretty inelegant. I mean, do we really need this intermediary text file that's no longer necessary after redirect runs? Luckily, we can avoid this extra text file using what's called a pipe. If I say /hello pipe /redirect, then the standard out of the program on the left, in this case hello, will be used as the standard input for the program on the right, in this case redirect. So let's run this. There we go. We can see that the output of hello was used as the input for redirect. By stringing commands together using pipes, we form what's called a pipeline, since our output is essentially moving through a sequence of commands. Using pipes, we can do some cool stuff without needing to write any code at all. For example, let's say we want to know how many files are inside of this directory. Using a pipe, we can combine the ls command with the wc, or word count, command. ls will output each file in the directory to standard out, and wc will tell us how many lines were given to it via standard in. So if we say ls pipe wc-l, supplying the -l flag to wc to tell it to count lines, we can see exactly how many files are in the current directory. So let's take a look at one more example. I have here a file called students.txt with a list of names. However, these names aren't in any order at all, and it looks like a few names are repeated. What we want is a list of unique names in alphabetical order saved to a file called final.txt. We could, of course, write a C program to do this for us, but it's going to get unnecessarily complex pretty quickly. Let's instead use pipes and some built-in tools to solve this problem. The first thing we need to do is read the file students.txt. The cat command will do just that. We'll read in the specified file and write its contents to standard out. After we've read the text file, we'll want to sort the names. The sort command can handle this for us. Sort will output the lines supplied via standard in to standard out in sorted order. In order to supply the contents of students.txt to sort's standard in, we could use a pipe to combine cat and sort. So I can execute cat students.txt pipe sort and press enter. And now we see the contents of students.txt in alphabetical order. So let's add another command, uniq, or unique, to our pipeline. As you might guess, unique, when supplied a sorted sequence of lines via standard in, will output the unique lines. So now we have cat students.txt pipe sort pipe unique. Finally, we can save the output of the pipeline to a file via cat students.txt pipe sort pipe unique greater than final.txt. So if we open up final.txt, we have exactly what we were looking for, a list of unique names in alphabetical order saved to a text file. By the way, we also could have said sort less than students.txt pipe unique greater than final.txt to do exactly the same thing using each of the operators we've seen in this video. My name is Tommy, and this is CS50.